integrated circuits. Okay, it's a bus interface connection protocol which you could communicate other devices or other integrated circuits through this protocol. Okay, so when you go for communication protocol, you have I2C, SPI, and serial peripheral interface, and you have UART, universal address receiver transmitter, which we have already completed. So I2C, it supports only 2 wires. Okay, it needs only 2 wires to communicate, and it can support up to 1008 peripheral devices. By using these 2 wires, you can connect 1008 peripheral devices, which is very quite high when you compare with other protocols. Okay, when you compare with the serial peripheral interface or the SPI, like it needs multiple chip select lines. So which will, whenever you have to increase the number of devices, you need additional number of lines for chip select. Okay, to select the devices. So that's one disadvantage of SPI. So on UART, like you cannot connect more number of devices as it will lead to bus contention issue. Okay, so through SPI, through I2C, you can connect up to 1008 peripheral devices. Like you can connect devices like EEPROM, temperature sensor. Okay, so if that device supports I2C, then you could connect by using these 2 wires. Okay, one is serial clock, the other is serial data. SDA stands for serial clock and SDA stands for serial data. So you can have multiple controllers and multiple peripherals. So you can have multiple master in this. So any device can be a master. Okay, so the disadvantage of serial port is whenever when you go with more number of devices, it cannot connect multiple devices as the bus will lead to contentions. Okay, bus contentions. When 2 devices attempt to drive the same line at the same time, then it leads to bus contention. So that's a disadvantage of the serial port. Whereas SPI, like it needs more number of chip select lines. Whenever you increase the number of devices, like 4 devices, you need 4 chip select lines, 4 GPIO. If you have 10 devices, then you need 10 GPIOs to select. Okay, and I2C is open drive. Open drive means they can pull the corresponding signal line low, okay, but it cannot drive it high. So by default, the line will be high. Whenever it wants to send a signal, like it will drive it low. So that's open drive. So I2C is open drive. So you have to configure whenever you go for the configuring the GPIO registers, it has to be configured. The output type has to be configured with open drive. Okay, and it needs the pull-up resistor. Like you can have the internal pull-up resistor when you could use a pull-up pull-down registers in the GPIO registers. You could use pull-up pull-down, and you could have the internal pull-up resistors. Okay. So coming to the features of the I2C, it's half duplex communication protocol. Bidirectional is possible, but not simultaneously. And it is a synchronous communication. It means it needs clock. It's a clock-based communication. The data is transferred in the form of frames or blocks. Okay, and it supports arbitration. Arbitration means it supports like multiple master bus system. So it means like whenever it can do like whenever an SDA line is found high. So it means the master one of the masters is active. So the other master will stop the transfer of data. Okay. So once the master sends a communication and like when it releases the SDA line, then the other master will take control of it. Okay. So it has an arbitration to supports multiple masters on the line. And it's due to serial transmission. It is used only for low speed communication. It can communicate only less number of data because it's serial. Okay, and clock stretching, like whenever the device is not ready, the master will raise the clock line. Okay, whenever the device is not ready to accept more data, by holding the SCL line low. Okay, so hence disabling the master to raise the clock line. So that is called clock stretching. So first I'll show you how it works. Okay, you have the start condition and stop condition. Okay, when the SDA line goes low and SCL is high, like this condition is called start condition. Okay, so when SCL line goes high and SDA from low to high, it's from high to low. So when SDA comes from high to low and SCL is high, okay, then it is start condition. The stop condition is when SDA is going high to high to low and you have the high signal, so that is stop condition. Okay, so this is how it works. First the master device sends a start condition. First you have to start the condition, then it sends the 7 address bits or 10 address bits of the slave device to be targeted. Okay, so it sends the address of the slave to be targeted. Every slave will have an address. Okay, every devices which is connected to the master will have an address. So it sends the 7 address bits which corresponds to the slave device to be targeted. Okay, when the master device sets the when it sets the read or write bit to 0, which signifies the write. Okay, so now there are 2 conditions. One the slave, when it founds the matching slave. Okay, else there is no slave. If no slave devices matches with the address, then the acknowledged bit stays at 1 by default. Okay, so it means the master has not found the slave, so the identification is unsuccessful. Okay, when the master finds a slave, then it receives the acknowledgement bit to 0. Okay, then it sends the data. But once it gets the acknowledgement, okay, then it sends the data is sent and data is acknowledged. Again you receive an acknowledgement to the master. Okay, again the slave sends the acknowledgement to the master. So here is the condition, like this is the start condition. So it sends the address bits and check for acknowledgement whether it is getting acknowledgement or not. Okay, if the slave found is if the master found the slave, then it gets the acknowledgement. Then it sends the 8 data bits, wait for the acknowledgement. Okay, and then once the acknowledgement is received, then it stops the condition. Okay, then stop condition. So this is the timing diagram. So you'll be very clear like when we write the program. So let's go for the program. Okay, so this is sending data to a slave device and reading data from a slave device. Okay, here master controls the ST line. These are controlled by the master. The device slave address 7 bits and looks for the read write, gets an acknowledgement, read or write. Okay, gets an acknowledgement and send the data bits. Gets the acknowledgement, again stop. Okay, now let's go for let me open the STM32 cube. So I will open the same folder on the date 26 demo. So I have used ADXL345. Okay, so in the data sheet folder, let me check the data. First, we will open the required data sheets for this project. So I have downloaded ADXL345. Okay, so this is the data sheet. Okay, this device has also have memory map. So if you check for memory map, so I had downloaded the ADXL345. Like you have to choose the right data sheet for this. like you have register map here, page number 24. Okay, let me check the table of contents, page number 24. Okay, so it has all the registered definitions, as like the controller, like it also has the registers, like you have register for read, write, latent. Okay, so you should be aware of this data sheet. You have to go through the data sheet entirely. We'll be using this register in our code, and the modes, like it has the detail about the modes. The one more data sheet is in the STM, like STM32, like STM32 user manual, like where the GPIO data sheet. Okay, how to go through the GPIO registers, RCC registered, GPIO registers, and I2C registers. So I2C, like it has I2C registers here. So you need to go through the data sheet of general purpose input output, because I2C pin, it will be the alternate functions on any one of the GPIO. So we have to configure this GPIO registers. In GPIO registers, we'll be configuring the GPIO port mode register to whether it uses the alternate function mode, because it uses the alternate function mode. So we have to configure 10 alternate function mode. Okay, so and then like you have to enable the bus, like just go through the block diagram. You have to find out which I2C was connected to which bus. Okay, as like you have to find out the bus, and you have to enable the clock for that bus. Let me show that. So here it is, the block diagram. Okay, so you have to find out which block diagram, like it is which block it has been connected. Like it is connected to ABP-B1. Okay, I'm going to use I2C1. So that is I2C1, I2C2, and I2C3. We are going to use I2C1. So once you identify the I2C1, you have to find out which pin has been, because it will be multiplexed. So I2C1 will be on port B. Okay, it will be on port B. So you have to find out which pin it has been multiplexed, and you have to set the alternate function. You have to set the alternate function registers, the appropriate pull up and pull down registers. Okay, and you have to configure the I2C data registers. I'll show you that on the program. Okay, so file new, I just create a STM32 project. Okay, so first you have to choose the board selector and give the board. Nucleo F411RE. Choose this board, click next. I put I2C, finish. Okay, just go for the main file. Okay, so the first thing is you need to include the hash. You have to include the header files. So I will use the same. Okay, and right click, go for properties. You have to set the path on the C++ build settings. You have to go for include path, and you have to set the path of the file system, like what are the files which you have to include. Okay, you choose include, select folders. Okay, file system. Okay, apply and close. Yes, click apply and close. Right click, build the project. Let me check for the error. Like, you need to declare this one. Open declaration. How to copy this? How to copy? Right click, properties, go for the preprocessor and click. Okay, you have to add the symbol. Click apply and close. Okay, right click, build the project. It should work now. Okay, so the build is successful. So let's write the code for I2C. Okay, so first you need to identify which pin it has to be. The I2C pin has been connected. Okay, for that you have to open the data sheet. You have to find out the pins. Just go for the GPIOs. Okay, and you have to find out the I2C pins. Okay, so you have to find out the pins. So you can note down the page number, like whenever you go through, like in order to avoid searching, like you could note on the page number so that it will be easier for you to refer it back again. I think it must be on the other data sheet. So we have to enable this APP-B1 as well as this AHB, both the thing we need to enable. Okay. Check for the alternate functions. Okay, here is the alternate function pins are there. Okay, so we are good. We have selected I2C1. Okay, I2C1. So I2C1 is here. I2C2 is here. Okay, I2C2, I2C1. We have choose I2C1. Okay, here it is. I2C1 is PB5 and like SCL is PB6 and PB5. Okay, and SDA is PB7. So PB7 and PB6. So I2C1 is PB6 and PB7. So you have to identify this, and we have to change here. Like, we are going to connect this pin to okay. Let me cross check once. It is PB7. I2C1 SDA is PB7. Okay, I2C1 SDA is PB7. And I2C1 SCL is PB6. Okay, PB6 is SCL. I'm going to connect PB6 as SCL, and PB7 is SDA. Okay, so let's write the function for first. Let us write the function for the init, bus init. So I just create a function called void I2C1 underscore init. Okay, so I just create a function for the initialization. So first we have to enable the RCC like AHB1ENR. Okay, so first we need to enable the GPIO-BN. Okay, so you have to define hash, just create the symbolic name. So you have to enable this GPIO A. A is 0, GPIO A is 0. So you have to shift 1. Okay, 0. B is 1. GPIO B is 1. Okay, so has defined like I2C1EN is 21. Okay, you have to enable the I2C1EN. Let's check for the bus init function. This is to enable the, you have to enable the clock access. You have to enable the bus. Okay, you have to enable the clock access to port B. To port B, because port B is connected to I2C1. Okay, I2C1. So first is AHB1. Then you have to set the pin as alternate function. Set PB6 and PB7 as two alternate function. Okay, to alternate function. So that is GPIOB. So mode R. So mode R. So I have already noted down the values. I'll show you. It's same as like the previous one. Like you have to locate the pin. Okay. So this value you have to get from the data sheets. So to set the alternate function, to set the 1 0, you have to configure 1 0. Okay. So GPIO mode, this is mode R. Okay. So we have set this pin to alternate function. Similarly for PB7. (18) and 19. Okay. So now you have to set output type as open drain. Okay, output type as open drain because I2C is open drain. So GPIOB what type R. Okay, so this value you can get from the register itself. The definition you could get from the register, from the registers. Okay, so open drain, I'm just declaring this as open drain. Both open is open drain. This is 1U. Okay, this is 1. U stands for unsigned. Okay, then we have to set pull up and pull down. We have to set pull up for both PB6 and PB7. Okay, so GPIOB, we put pull up PUPDR is a register. Okay, so set the pull up. Set the pull up resistors. Okay, we have to set output type as open drain, and we have to set pull up for both. And it should be negation because it's 0. Okay, so then we have to set the alternate function type. Set the alternate function type for I2C. So GPIOB A for 1, okay, and negation of okay. So this is for the alternate function type. I'll show you in the data sheet. Similarly, like what you have to set for the alternate function type is for what it is AF07. Here it's AF04. Okay. So this is for PB6 and PB7. Copy this, and here you have to change from 4, 5, 6, 7. Okay, 4, 5, 6, 7. Okay, so we have set up this value, like check RCC. Now we have to enable the APP peripheral bus, APP1 ENR equals I2C1 EN. Okay, have to enable the bus, have to enter to reset mode. First you enter the I2C1 to reset, and then you clear back again. Okay, this is to come out of the reset mode. It is software reset. So copy this, negation. Okay, this is to come out of the reset mode. You have to set the peripheral clock. Set the peripheral clock. Okay, peripheral clock frequency. It is 60 megahertz. So I2C1 CR2. Okay, I2C1 CR2 equals 4. Okay, it is 16 megahertz. This okay. So I2C1 you have to set on the CCR register, clock control registers, equals, I just define a name. You have to create the symbolic name for this. Okay, hash define. Okay, it's 80 for 16 megahertz. Okay, but I2C will be running, the clock will run at 100 kilohertz. The input is 16 megahertz. So set the peripheral clock. I2C1 T rise of so you have to set this bit SD mode max rise time. This value you have to take from the data sheet. Hash define, okay. Max underscore rise underscore time equals 17. Okay, so finally you have to enable the clock. You have to enable I2C on the control register. CR1, okay, equals CR1 PE. So create the symbolic name for this. Hash define CR1 PE. Okay. So we have completed the initialization. Let me compile the program, check for any error. Okay, so we have completed for I2C initialization. Let's write the program for read and write. Okay, but we will go for byte read. So we have to create a function void of I2C1, okay, byte read. So it will have 3 input arguments. One is the address. Slave address. S address stands for slave address. M address stands for the memory address. Okay. Char of data pointer. Data pointer, which is the pointer which has the data. Okay. So S address for slave address and M address for memory address and data pointer. Okay, so these are the 3 input arguments. So let's put while of, you have to wait until bus is not busy. Okay, first I will write all the steps. Wait until bus is not busy. So this is the first step. The second step is generate, once it is not ready, once it is available for transfer, generate start condition. So that is the second step. Okay, and third step, wait until the start flag is set. Flag is set. Okay, so this is the third step. And the fourth step, transmit slave address plus write. Okay, that's the fourth step. Now fifth step is wait until the address flag is set. Okay, and then clear address flag. Once the flag is set, it is clear. Then send the memory address. Okay, send the memory address. Okay, again wait until the transmitter is empty. Generate, once it is empty, you have to generate a restart. Generate it, restart. Wait until start flag is set. Okay, now transmit slave address plus read. Again wait until the address flag is set. Wait until the address flag is set. Okay, then once it's set, you have to disable the acknowledgement. Disable acknowledgement. Okay, clear the address flag. So these are the steps for byte read. Okay, once then you have to generate stop after data received. Okay, wait until receiver enable is set, RxNE flag is set. Then read the data from data register. So this is the step for reading the byte. Okay, we had write code for all the steps for data register. So before that, I just compile the program. Go for Windows, show view, click SFRs. You just drag and drop the registers. Okay, and you can find I2C1. So these are the registers: CR1, CR2, SR1, SR2, CCR. Okay, so you have to create a symbolic name for this CCR, CCR and SR1. Okay, SR1. So you have to create the symbolic name for all these registers. Like in order to set, like if you, for example, if you want to find out the BC bit, then you have to put SR2 BC. Okay, so let us create the symbolic name first. So to find whether to find SR2 BC, okay, first I will create the hash define. Just copy this. First I will create a symbolic name for the necessary registers. Okay, so hash define of SR2, it should be on capital. SR2 BC. Okay, this is for BC. Okay, so it's 0 1 U shift of 1. Okay, because it is in the position, it is here. Okay, from the LSB it is 1. This is 0 and this is 1. So MSL is 0 and this is 1. SR2 BC is 1 shift. Okay, then CR1 control register 1 start bit. So if you check CR1, the start bit is here. Start is here, 8. Okay, The start bit is at the 8 bit, so you have to put 1U, sorry, of 8. Then SR1 SB. Okay, so that's 1U, zero. Okay, so SR1 TXC, RXNE, you have to create for everything. Okay, for SB, whatever the thing which is required. In SR1, we need SB, ADDR, we need ADDR SB, ADDR BTF, hash define SR1 ADDR 1U shift of 1, okay, and SR1 TXC transmit enable 1U, okay, 7, okay, SR1 RXNE 1U of 16. So this value, this 16, the shift value 1716 is taken from here. Okay, for example, TXC, it is 7. Okay, RXNE, it is 6. Okay, RXNE is 6. It is not 16, it is 6. Okay, and BTF is 2. SR1 BTF. Okay, so you have to create the symbolic name first. SR2 BC, okay, CR1 start, there SR1 SB, SR1 address, TXC. Then we have to create for CR1. Just create CR1 start, we have CR1P also we have created. So CR1 acknowledgement and stop is there. Okay, just go for CR1 ACK acknowledgement and stop. ACK is 10. Okay, it's 10. CR1 stop. Okay. So we have created the symbolic names. So let's write the program. For okay, so first thing is you have to check for wait until the bus is not busy. Okay, so in order to while off, you have to put a simple while. Okay, while off I2C1, you have to get the register SR2. Okay, and the symbolic name is SR2 underscore BC. Okay, SR2 underscore BC. Okay, SR2 underscore BC. So then next is the generate start condition. I2C1 CR1 equals CR1 start. Okay. So we have started the start condition. Now we have to wait until the start flag is set. Okay. So in order to write the program, like I'm just copying the same code. Okay. This is the register is SR1. Okay. So SR1 underscore SB. Okay. SR1 underscore SB. So that's the register. So you have to check whether the start bit has been set. Okay. So now you can transmit I2C1 to transmit the slave address. Okay. And wait until the address flag is set. Okay. I just copy this, check until this address flag is set. Okay, ADDR. So here you need to check the not condition here. We have one more condition here. Okay. For this also not condition. Okay. And you have to clear the address flag. So to clear, like you move a temp variable, temp equals I2C1 of SR2. Okay. So you have to declare this temp. It's volatile int of temp. Okay. So we have created the temp. I2C1. So just send the memory address and wait until the transmitter is empty. So the flag is TXE. Okay, TXE. And you have to generate the restart. So to generate restart, it is CR1 okay, CR1 underscore start. Okay. So generate restart. So wait until the start flag is set. Okay, just copy this and paste it here. Okay, now you have to transmit slave address plus, right here, slave address plus read. So it is okay. So transmit of slave address plus read R of 1. Okay. and wait until the address flag is set. Copy this. Have to disable the acknowledgement. So to disable the acknowledgement, like you check for the I2C one, okay, CR1. So to disable the acknowledgement, CR1 SEK. Okay, so you have to disable the acknowledgement. Next, so you have to clear the address flag. Clear the address flag. Okay, so generate stop after the data. So you have to generate stop CR1 underscore stop. Okay, you have to generate stop. Wait until RxNE flag is set. Copy this and check for RxNE. Okay. Finally, you have to read the data from the save this on the data I2C1, sorry, I2C1 from the data register. Okay, so that's all. So we have completed the code for the byte read function. Let me check the, I'll build this and I'll check. This TMP is not temp, it's TMP. Okay. So the build is successful. Okay. So the build is successful. Now let's write the functions for, so far we have created, so I just defined the prototype here, like int, okay, byte read function. So we have, I just repeat the code. We have written the program for functions for initialization as well as byte read. For initialization, you have to choose the I2C. We have chosen I2C1. You have to enable the clock access for the GPIO and the peripheral clock. Okay, so high performance, you have to activate the high performance bus clock, which is connected to port B, and you have to activate the clock for the I2C1, which is the peripheral clock. So first I enable the GPIO clock, and you have to set the mode register for the alternate functions and set it as open drain. Set the both the GPIOs pull up. Okay, and you have to find the alternative function type for I2C, and you have to set those value on the registers, AF4 registers, and this is to enable the clock for APP B1 ENR for the peripheral bus. Okay, and you have to set the control registers. You set resets. This is for software reset. Enter to reset mode, clock, come out of the reset mode. Okay, set the peripheral clock frequency. It's 16 megahertz, and you have to configure the I2C clock as 100 kilohertz. Okay, and you have to enable the registers like CRP, so control registers, like you have to enable the I2C1. So, so once the initialization is done, then we have written the code for byte read. Okay, so two more functions are there. One is bus read, the other is the bus read and the bus write. Okay, so let's write the program for bus read. Okay, so I'll just copy this same thing. Okay, I create a function here. And I convert this to bus tree. Okay. And this is integer n. Okay. So what I'm going to do is I'm going to just copy this code from the byte sheet. Okay. And I'm going to paste till this acknowledgement symbol. Okay. So clear address flag. So clear the address flag. Wait until the address flag is set. Okay. So I will just copy from here to wait until this address flag is set. Okay. I paste it here. So wait until the address flag is set. You just clear the address flag. Okay. Clear the address flag. And then we have to enable the acknowledgement. Enable acknowledgement. So I2C1 of CR1. Okay. So CR1 ACK. So just put a simple while loop, while of n greater than 0, okay, U for unsigned. So we have create a while loop. So if n equals 1, we are going to have one function, else we are going to have the other function. Okay. So if n equal to 1, so we have to I2C1 here 1 have to disable the acknowledgement. Okay. Disable the acknowledgement, ACK, and generate stop. So I2C1 CR1, okay, for generating stop, generate stop. Okay. So you have to wait until the RxNE flag is set. Okay, have to wait until this RX. So you have to copy, just copy this. Okay, DR. So here, just copy this. And this condition like DR n minus, sorry. Okay, so this will continue. Okay. So we have completed the function for the bus tree. Similarly, like we have to complete for bus write. Okay. So I just copy the same code. Let me paste it for bus write. bus write, okay, of char data. So I'm just going to copy from here, like white CR1 start, okay, until clear. I just copy. Okay, so here after this you have to modify. So you put a for loop. Okay, put a for loop for int of I equals 0, I less than n, I plus plus. Okay, so you check for TXC. Okay, check for the BTF. Generate stop. Okay, so we have completed the code for bus write. Okay, so like once you practice, like you just write the code for 2 or 3 times, you'll get thorough. You'll be getting thorough in this one. Okay, so far, like we have completed the init byte tree, and we have completed the bus tree. Let me copy this bus tree and define the prototype on the top. Okay, bus tree and bus write. Okay, so I close this one. I build this project.